I have a question to you. Do you know when and what function these devices perform? No? Do you know someone? Yeah, right. It's a video phone. In 1929. Now you have much better performance system that is smartphone. Okay. So next question is who innovated smartphone? Yeah, there are several opinions. So in my opinion, the theorist, most important theorist is, I think, this person. Maybe a electrical engineering student has to run this equation, Maxwell equations. Uh, he established this four equations in 1864. 1864 is Japan in the late Edo period, the era of samurai. And this year was the President Abraham Lincoln's second term. So it's around the civil war. So the Maxwell in these equations, Maxwell predicted electromagnetic waves in vacuum, but he couldn't find it. The person who found the electromagnetic wave in vacuum is Dr. Heinrich Hertz. But he focused only on demonstrating Maxwell's prediction of electromagnetic waves using this system. It's a discharge. Okay. The person who innovated wireless communication is this person, the Guglielmo Marconi. He was the Italian electrical engineer and the inventor, and he succeeded the Purdue, UK, and the Signal Hill, the part of Canada, 3,500 kilometer radio transmission in 1901. So he was the true pioneer of smartphone today. And do you know this person? He was the Brown. He developed Schottky diode, metal semiconductor junction in 1874. So, but soon after his findings, John Fleming, invented the diode tube. It's a vacuum tube. And in 1906, Reed Forrest invented the amplifier tube. So the era changes from the solid state semiconductor to the vacuum tube. Okay. This is the photo of transceiver in Japan. And the age returned to the solid state in 1974, 1947. Shockley Bradin invented the contact bipolar transistor. So now we are in the semiconductor era. Okay. If we look at the lighting, by 19th century, the frame was the lighting source for human. It's an oxidation of hydrocarbons. And in 1879, incandescent lamp was invented, which is the so-called black body emission. It's inefficient in terms of the visible light. And in 1926, fluorescent lamp was generated, but it was the glass tube, so it is brittle. And 1962, practical LEDs was invented at the University of Illinois. So the 1996, the new star, the solid state lightings was commercialized. As I mentioned yesterday, the contribution of gallium nitride-based LED lightings for energy savings is huge. Okay. According to U.S. Department of Energy, the people in the United States can save about 22.9 petawatt hour from year 2017 to 2035, which correspond to 890 billion US dollar, which is huge. So what is next? The students try to invent a new system, which is try to connect human and internet. Okay? The display once the PC display was fixed, but smartphone is movable, but your hands are not free. So sometimes this kind of thing happens. Okay. If you can establish this kind of displays, eyeglass type display, it's movable and your hands are free. So our students are trying to develop a new interface systems. Okay. We need a high definition. In the daytime, more than 10,000 pixels per inch is necessary. And in the night, it is more than 30,000 pixels per inch is necessary. And there are several candidates, LCD, liquid crystal displays, OLEDs, and micro LEDs. And we, of course, are trying to focus on the micro LED application. This is high luminous efficacy, high brightness, the long lifetime, and high response speed. Okay. Yeah, there are several expected advantages, but uh, fabrication is, of course, very, very difficult. There are two approaches, bottom-up approaches and top-down approaches. Bottom-up is from the crystal growth. We grow each pixels. So full color means we need three different LEDs. And the top-down means after growing LEDs, we etch pattern to form the arrays. The top-down approach is the scalable and manufacturable. But we found, the students found that the etching damage is very, very serious at the sidewall. So the carrier transport to the sidewall and it combine. So now we're selecting the bottom-up approach. Okay. Let me show you some example of the results. The Mr. Kai, now the PhD, trying to establish a new growth procedure, which is the selective area growth by MOCVD. Okay. Please look at the size. Size is 360 nanometer. Okay, which is very, very small. And what he found is after growing gallium nitride, he deposits this platelet, indium gallium nitride platelet. And the scanning TM image shows there is no dislocation. Even the lattice mismatch is more than 5%. and there's no interdiffusion of indium and gallium, and there is no misfit dislocations. Okay. And the interesting thing is inside this indium gallium nitride platelet, indium composition changes from the bottom to the top. Indium concentration increases up to 30%. And along this scan, the indium composition is rather stable, but the bottom side indium composition is small, and the top side indium composition is high. Indium content almost linearly increased from 15% to 25%. Indium content fluctuation is around 25 to 30% at the top and 70 to 80% at the bottom. Of course, the growth condition is constant. He never changed the growth condition. So linearly increased indium content is related to strain, reduced strain. Okay? The composition is like this. And also what we found is this is maybe you know this X-ray diffraction reciprocal space mapping. This is without indium gallium nitride. This is with indium gallium nitride. This is the in-plane direction. This is the out-of-plane direction. Okay, and this is the gallium nitride diffraction, and this is the indium gallium nitride diffraction. So it seems the lattice is inclined. Okay, this means if there is a misfit dislocation, it easily occurs. But we don't see any misfit dislocations, which means that lattice is expanded like this. This is a very interesting and new results. And we observed the red emission. Okay. Uh, this is not a good indication, but the IQE, if we compare the low temperature and the high room temperature intensity, the internal quantum efficiency is around 20%, which is not so bad. So next, how to operate these tiny pixels? Okay. First, we try to put the arrays onto the silicon CMOS driver. But we found that it was very, very difficult to align. The array is more than 1,000 and 1,000. And then aligning onto the CMOS driver, it was very, very difficult. So, and also the silicon CMOS driver is very, very expensive for the university people. Therefore, the young researchers try to grow the drivers and LEDs in a one MOCVD planning. This is the process flow. And he first grew the gallium nitride, aluminum gallium nitride hemp structure, and then grew LED structure. Okay. So N-type is the hemp. And then he fabricated these circuits. Okay. Each LED, he has two hands, selected transistors and drivers, drive transistors. And yeah, at present, it's a very initial stage. So we only achieved 2 by 2 uh, pixel arrays. Okay. If the low is -5 volts and the current is 0 volt, we can turn off the LEDs. Okay. This case, the -5 and the 0, -5 and 0, and -5 and 0. Okay. Uh, Next, I'd like to show you the another young researchers' activity for solid-state terahertz oscillation oscillators. Maybe in future, the terahertz sensing technology is essential for the safe right. And we are interested in the IMPATT diode. uh, Impact ionization avalanche transit time diode, which is the two-terminal high-frequency oscillator. Okay, and then the reason why we are interested is because of the high power at high frequency. Okay, uh, according to the theory, this is the silicon limit, and the gallium arsenide limit is here, and the gallium nitride limit is much higher. The reason is the large band gap, the high critical electric field, and the high electron saturation mobilities. Okay. And there are several reports of the gallium nitride impact diode, but majority of the reports were only simulation. Only one experimental result reported by Professor Shravanti Chaudhary's group, the Stanford University. It is the actual 800 megahertz. So young student Kawasaki, he tried to develop the new gallium nitride impact diode, the P plus N, very simple PN junction diode. This is grown by MOBP, and he carefully controlled the N-type donor concentration. It in average 8.6 times 10 to the 16th. And the breakdown voltage or avalanche breakdown occurs at 315 volts. Okay. And this is the measurement setup. The It's a power supply, a resonant cavity, impedance matching, and sub tuner, and the waveguide. And the CAM package was installed here, and then it is the adjustable short, and the microwave is emitted from here. And we set the DC bias very close to the average breakdown, and then put this modulation voltage, we can observe the oscillation. This is the result. The first trial, he succeeded up to 21.1 gigahertz. The power was not so bad. It's 8.36 watts. But the efficiency was very low, only 1%. So next, he tried to optimize the structures, the so-called high-low structures. From this equation, we found that the DC voltage across the average region should be low. and the thickness also should be thin. So we have to optimize the thickness of high region and the low region, and also the impurity concentrations. Okay, so these are the avalanche region, and these are the transit carrier transit regions. The requirement is, for example, the low breakdown voltage and the thin avalanche region and the band-to-band transition. Okay. So high region, we should consider the tunneling. Yeah, the tunneling causes the leakage. So we have to be careful about the doping concentration of high region. The concentration of high region is 2 times 10 to the 17th per cubic centimeter. Okay. Then by controlling the high region's thickness, high efficiencies can be expected. Okay. We can realize over 20% efficiency in theory. So he tried to fabricate this high-low structure IMPATT diode by controlling the low layer doping 1.5 to 3.3 times 10 to the 16th. It is very, very precise. Okay. Yeah, he succeeded to improve the efficiency, but still it's 2%. It is very, very difficult to improve the efficiency of IMPATT diode. Okay. Yeah, this is the silicon gallium arsenide CW and pulse limit, and the gallium nitride expected to be much, much higher out power and higher frequency. But it was very difficult. What we achieved is up to 36 to 37 gigahertz. The problem is, in case of IMPATT diode, we bias the reverse bias, very high reverse bias. And if it is turned on, the high density current is flowed. So our expectations shows that the junction temperature exceeds 600 centigrade. So now we found that it was very, very difficult to improve the efficiency of the IMPATT diode. The sample group also demonstrated a higher efficiency, 60.8 gigahertz oscillation, but the power is limited to be 18 milliwatts. So the red one is our result, and the Stanford result is here. This is our students' achievement. So if you are interested in, please join our group to improve the efficiency of two-terminal high frequency oscillators. The third topic is the application in space. There are a lot of particles in space. The charged particle like proton beam, electron beam, heavy particle beams, and uncharged particle, the neutron rays, gamma rays, X-rays, ultraviolet rays. So we try to apply the new device for power electronics to be protective against displacement, damage those total ionization, those or single event effects. If we compare the silicon radiation had MOSFET, gallium nitride hemp is superior by a factor of 30. This is the EPC results. Okay. And compared with gallium arsenide, this is LEDs. The gallium nitride LEDs is very, very strong against the radiation hardness. This is gallium arsenide LEDs, and this is gallium nitride LEDs. Hence, compared with gallium arsenide, gallium nitride has superior for space applications. The resistance gallium nitride power hemp have been already demonstrated by Sumitomo Electric. The normally off-type power hemp, the Casco type is not good because we have to use the silicon gate driver. Okay, so P-gate would be better. And the critical dose have been already demonstrated: electron 10 to the 16th, proton 10 to the 13th, heavy ion 10 to the 11th. So, for example, electron beams exposed to geostationary satellite over 10 years have been expected by gallium nitride hemp. So, I can say that gallium nitride, aluminum gallium nitride hemp is the most promising device for space applications. Now, the students are trying to develop wireless power transmissions on the moon. Okay. This is the collaboration of NGK, NU, Kanazawa Institute of Technology, and Komoto University. So, these are our members. It's an wonderful comprehensive team from materials or bulk crystal growth, the epi growth, the circuit design, the module design, and the system applications. And we have the 57 companies and 21 universities and 2 research institutes. ICE and the NIMS are joining our consortium. And we have the R&D strategy management team only for gallium nitride. Okay. So if we are interested in our activity and want to perform collaboration with us, please do not hesitate to contact me. Thank you so much for your kind attention.